Can't?
I think now we are alive.
Okay.
Yes.
Okay, let's start. First of all, good afternoon, everyone. It's a pleasure to receive you today. I would like to introduce you, Dr. Vladimir. Okay, have a seat, please. Close. I would like to introduce you, Dr. Vladimir Schwarzman, from University of Duisburg, Essen, in Germany. If I remember, Dr. Schwarzman has a PhD in physical chemistry.
Yes.
Physical chemistry from Rudolf Institute of Physical Chemistry in Moscow. Karpov, I'm sorry. Okay, he was born in Russia. It's easy for him, but for us it's very difficult. Okay, I'm sorry. So, Professor Vladimir will talk today about any specific point regarding ferroelectric and the recent advances on the development for materials for energy storage. Okay. Next week, Dr. Schwarzman will give a short course. Okay, a short course from Tuesday up to Friday. Probably Professor Fauzi will send an email for everyone. Okay, but next week for the PhD students of the material science program, I think will be valid for credits. Is it correct? Okay. So just now I will ask for Professor Schwarzman. As we told in Brazil, as we say in Brazil, your aircraft. Okay.
Okay. Thank you very much for the introduction, and thank you very much for inviting me to visit Brazil and this nice city, Ilha Solteira. So mine was actually my first visit to South America, and I really enjoyed staying here. And that was something I think Professor Auer for this opportunity. So I come from Institute for Material Science at the University of Duisburg, Essen, and I will give a talk today about ferroelectric and related materials for electrical energy storage. But before I will start my presentation, just to shortly show you where I'm from. Sorry, this is map is in Russian, but this is Germany, and we are from here. So this is the region. It's a some kind of magnified image, and you see this red. It's all cities. So we are from so-called Ruhr region in Germany, which was actually heart of the steel and coal mining industry in Germany in the 19th and first half of the 20th century. And this is, I think, one of the largest, or maybe the largest, metropolitan agglomeration in the world. So these are all big cities. Essen is here, Duisburg is here. Both cities have approximately 500,000 of inhabitants. Government is also great, so you know, maybe since you know football, you know Borussia Dortmund. So they're from here, but we are from Essen and Duisburg, and these were two different universities which were joined together in 2003, and this is image of Essen. So quite a modern city. This is famous coal mine, Zollverein. It belongs to the UNESCO World Heritage List as the most beautiful coal mine in the world. And this, we don't have only this, and this we also have green areas. Also, this is the Ruhr River, and this is make kind of lake. So you see nice green areas in this list also. So Duisburg Essen University has campuses in Essen, campus in Duisburg, merger 2003, and belong to 10 largest German universities. is not most actual numbers, but we have approximately 40,000 students in our university, and among them about 10,000 first-year students. The main research area are nanoscience, biomedical science, educational science, urban system, and transformation of contemporary societies. So when we are actually also in the Faculty of Engineering, and actually we are in the Department of the Civil Engineering, our Institute of Material Science. This is our group. You see, this photos was made not so far away, a long time, in Corona time, and therefore we all have here as mass. So presently we have 24 members of the institute, among them 30 PhD students, and our main research areas ferroelectrics and related materials, hybrid perovskite materials for solar cell application, high temperature ceramics in thermal insulation, recycling of cement, and quite exotic but interesting mechanics of Antarctic sea ice. So I myself involved in these two first research areas. So and I will speak today about ferroelectric for energy applications. So this, I think, that contribution of renewable energy sources such as solar, wind, and geothermal energy is growing. So you can see, comparison for 35 years ago, the percentage of these energy sources is increasing. But the problem is that most of these energy sources are intermittent in nature, and therefore this is making big challenges to harness the sources of energy. Therefore, we need to develop not only devices to earn the energy, but also devices to store the energy. So we need efficient and reliable energy storage solutions to implement the electricity generated from this renewable energy sources. So, and here is a diagram which shows the relation between the energy density and power density for different energy, electrical energy storage approaches. So it's batteries, electrochemical capacitors, etc. And what I will speak about is in this range is electrostatic capacitors. And you may see from this diagram that in sense of stored energy density, they are not the winners, but they have much higher power density in comparison to all other systems. So electric capacitors can release the stored energy in an extremely short period between microsecond to millisecond, and therefore generate an intense pulse of current or voltage. Moreover, in comparison to this system, electric capacitors typically are much robust and much stable, both in relation to applied electric voltage and thermal and mechanical stability. They can be operated under several hundred to thousand volts for longer duration and large number of charging, discharging cycles. So, this is outline of my presentation. First, I will speak about basic parameters of energy storage in dielectric capacitors. Then I will speak about energy storage in so-called relaxor ferroelectrics, antiferroelectrics, and polar polymers. And finally, I will summarize my presentation. So, basic parameters. So, when we take just a classical dielectric capacitor and apply a voltage U between these capacitors, we can store a charge on the metallic electrode of this capacitor, which is proportional to the applied voltage U. And for this simple plain parallel capacitors, it's well-known relation for the capacitance. It's proportional to the dielectric permittivity, area of electrodes, and inverse proportional to the thickness between the capacitors. And when we now will speak about which energy we will store by this capacitor, this will be just simple expression. 1 1/2 charge multiplied to voltage, or 1/2 capacitance multiplied to the voltage square, or the density, when we will normalize it to the volume, will be proportional to the dielectric permittivity and square of the applied electric field. So this is illustrated here when we have charge in the y-axis and applied voltage in the x-axis. So the stored energy will be given by the area between our charge voltage linear dependence and the axis of charges. Of course, when you can see on this equation, it's clear when we have a dielectric with a large dielectric permittivity and we can apply to this capacitor large electric field, we can store more energy. So typically linear dielectrics have very small dielectric permittivity around of 10, the relative dielectric permittivity. Therefore, it's interesting to go to other materials, the ferroelectric materials, which have much larger dielectric permittivity. It can be 1,000, even 10,000. So ferroelectrics, just by definition, are materials that have a spontaneous polarization. So not only induced polarization like in normal dielectrics, but even in the absence of the electric field, they possess the polarization. This is PR, and this polarization can be switched by application of, let's say, specific electric field, which is called coercive field, and we can change the direction of polarization. And typically for ferroelectrics, we observe such a characteristic hysteresis polarization loop. So the ferroelectric state usually occurs below so-called Curie temperature, when in our material we have a structural phase transition, and the structural phase transition in some cases is accompanied by appearance of the long-range polar order of ferroelectricity. So above Curie temperature we have so-called paraelectric state, polar disordered state, and below Curie temperature we have polar ordered ferroelectric state. So now when we go to the ferroelectric, we will speak now not about charge but about polarization, which is actually not nothing else as charge divided to the area of electrodes. And we speak not about voltage, but we speak about electric field. And this is our example of our hysteresis. In that case, again, so to calculate the stored energy, we have to integrate the area, let's say, between the polarization axis and charge order discharge curve. So when we consider the area between the charge curve, this, so it's a total stored energy in our ferroelectric capacitor. But when we now discharge our dielectric, you see that the area, the energy which we will obtain is smaller, and this energy between the discharge branch of the curve and the polarization axis is called recoverable energy. So we have stored energy, we have recoverable energy which is less, and the difference actually is given by area of this hysteresis curve, which is nothing else as the energy loss density. So one can consider it as a stored energy or recoverable energy density, and consider also this parameter which is called energy stored efficiency is actually a relation between recoverable and stored. So when eta is close to 1, it's optimal case, all stored energy can be used again. So how we can measure this stored energy or recoverable energy? Typically people use the Sawyer-Tower circuit to observe the polarization hysteresis loop, and sometimes people analyze bipolar hysteresis loops, and from the area between the, let's say, again, charge or discharge curve estimates the area, the corresponding energy density. More correct is to use the unipolar hysteresis loop, so when it cycles the electric field only from 0 to the maximal value. since again we have not only the electric permittivity, we have also electric field as parameter which determines the stored energy density. So our materials, to be good for application, has to withstand the high electric field. So they have to have so-called large breakdown strength. So this is critical field when the dielectric breakdown occurs. How it's measured? Typically, we have many materials, then we bring them to the breakdown event, estimate the electric field where breakdown take place, and then make such a called Weibull distribution. And from this Weibull distribution, we estimate the parameter EW, is our breakdown strength. And breakdown strength depends on many parameters: temperature and humidity, time profile of the applied field and test duration, size and shape of electrode, sample thickness, chemical composition, microstructure of the materials, like grain size, pores, defects, interfaces, etc. And when we speak about main or most important mechanism of the dielectric breakdown, it can be electronic breakdown. So when we apply so high electric field that we can induce the transfer of the electrons from the valence band to the conduction band, or the also transfer of electrons from the defect levels inside of the band gap to the conduction band. So, and when we have enough electrons, we can come to such a called avalanche breakdown event, when three electrons interact with atoms and they, let's say, expel another electrons, and we have increasing number, and we have kind of avalanche effect. So this breakdown strength depends on the energy of the defect level relative to the conduction band. In that case, when we have avalanche effect, so this is kind of intrinsic effect, this is also, but this is more or less depends on the thickness of the sample. Of course, when we have a thick sample, probability to have an avalanche will be high. When we have a thin sample, since the electron will have in a thick sample more possibilities to interact with other atoms. So therefore, for example, the breakdown strength of the ceramic samples is always smaller than breakdown strength of the films of the same composition. So we can have also electromechanical breakdown, since when we have electric field, we always have electrorestriction, and sometimes in ferroelectric we also have piezoelectric effect. So we have a compression of our material under action of the electric field, and this compression may result in the mechanical stress, and this mechanical stress will also result in the breakdown. And finally, we can have a thermal breakdown mechanism, since any current which flows through our material will induce heating of our material due to the Joule length effect. And when the heating effect is less than the dissipation of the generated heat, finally we come to higher, we will heat our materials, probability of transition of electrons to the conduction band will be increased, and breakdown will be easier. So these are main mechanisms. And just to illustrate how this depends on microstructure, so you see when we have a grain size, so typically breakdown field in fine grain ceramics is higher than in the coarse grain ceramics. The thickness I already mentioned, so avalanche effect is breakdown strength is inverse proportional to logarithm of thickness, and therefore when we come with the bulk material, when we come from the thin film material to bulk material, our breakdown strength will decrease, and dielectric permittivity is also not good, so high. This is the intrinsic moment. So to have good energy storage, we have to have the large dielectric permittivity, but on the other hand, the large dielectric permittivity will decrease our breakdown stress. So currently we have to also always deal with the interplay between these two parameters. Okay, so what we have to do to make a good material for energy storage application, we can do either fine-grained ceramics or film, or the best, we can go to the multi-layer capacitors. Since, again, when we speak about, I speak about energy density, but what we need in application, we need energy. So not density, but energy itself. And of course, when we have a thin film, we can store a lot of energy density, but the volume of thin films is small, and therefore energy stored will be small. Therefore, from films, we have to move to multi-layer capacitors. So, again, this picture, energy density and high energy storage efficiency require large difference between the maximal induced polarization and the remanent polarization, small hysteresis, and large breakdown steps. So this is actually three main criteria which drive people to look for optimal dielectric material for energy storage. So, linear dielectrics, almost no hysteresis, almost no remanence, but very small induced polarization, therefore they are not good. Ferroelectrics, very large induced polarization, but also large remanent polarization. And therefore this area in here is actually small, and we have a lot of losses due to the hysteresis. Therefore, people don't look for the ferroelectric material as the energy storage material, but they look for two, let's say, related materials families. One is so-called the relaxor ferroelectrics, which has large induced polarization, small remanent polarization, and also very tiny hysteresis, very thin hysteresis loop, or antiferroelectric material, which in ideal case have actually zero or very or negligible polarization at zero field, against strong induced polarization here, and the area will be even larger than the relaxor ferroelectrics, but also they can have large losses due to this finite hysteresis. In my next, let's say, time, I will speak more about the relaxor ferroelectrics, antiferroelectrics, and polymers. So, relaxor ferroelectrics. What are relaxor ferroelectrics? I think for most of you, it's a new term. So, normal ferroelectrics, I already introduced materials which have spontaneous polarization, which can be switched by electric field. And these materials have a long-range polar order below the Curie temperature. We can see macroscopic domains, region with polarization, for example, in one or in opposite direction. And typical dielectric permittivity versus temperature for normal ferroelectrics look like here. So we have a sharp peak at the Curie point, and above this Tm, our dielectric permittivity follow well-known Curie-wise law. And when we now come to relaxors, we see differences. So instead of such a sharp peak at constant temperature, we have in the relaxors very broad peak of the dielectric permittivity, and position of this peak, this Tm, is not constant, it strongly depends on temperature or on frequency of applied field. Moreover, the Curie-wise law above Tm is not fulfilled. So, instead of such a square, let's say, like polarization, hysteresis loops with large remanent polarization, the relaxor show a slim loops with thin hysteresis and very small remanent polarization. What is even more interesting, these loops are observed in relaxors not only below Tm, but at temperatures much higher than Tm. And even more interesting, in the normal ferroelectrics, this maximum dielectric permittivity corresponds to the structural phase transition, and in the relaxor, no change of the structure happens at Tm. So it was proposed that such behavior of relaxors is related to the unique polar structure, namely to existence of so-called nanoscale polar regions or PNRs, which are short-range ordered, and they appear already at temperatures much larger than 10, and they stay, and they interact, and they slightly grow with time, with cooling, but finally, even when we go to the very low temperatures, they still remain in the nano-sized range, and no long-range order appear, but this short-range polar order is kept. So, like, this is a kind of, how to say, generally accepted picture of what happens in the relaxor ferroelectrics. So, at high temperatures, we have a paraelectric state without any correlation of the polarization. Then, on cooling, below so-called Burns temperature, we observe appearance of these polar nanoregions. Initially, they are dynamic. This means they easily fluctuate between the different polarization direction. When we apply the electric field, we can align them all in electric field and we have a large induced polarization. But when we remove the field, they go fast back to the disordered state. When somebody of you is from magnetism, in magnetism, similar behavior is called like superparamagnetic behavior. Therefore, sometimes they call it superferroelectric testing. So on cooling, they slightly grows, and they start to feel each other. They start to interact, and finally, the dynamics of PNR is slowing down, and this peak of the dielectric permittivity, which observed, is actually related to the slowing down of this PNR's dynamic. And finally, below so-called freezing temperature, they become frozen. So, and we need really hard, large electric field to move them. And in some cases, we can induce the transition to the ferroelectric state, but in that case, this transition will be irreversible. So, when we have this relaxor ferroelectric material, so what we need? We need structural disorder. The typical example is lead magnesium niobate is a material which is so-called perovskite structure. Perovskite is the system of the octahedra. In the middle of the oxygen octahedra is one of the transitional elements. In this case, it's either magnesium or niobium, and in the octahedral voids there is lead in that case. So, what is interesting is that we have the same crystallographic position, so-called B position of the perovskite structure, which can be occupied both for magnesium 2+ and for niobium 5+. So we have in the same crystallographic position ions which can randomly have either 2+ state or 5+ state. Yeah, and this disorder, this structural disorder, is the source of the electrical disorder, also called random electric fields or random mechanical stresses. So sometimes we have cations with the same charge state, but of essentially different size, and this will result in these mechanical stresses. So this structural disorder is one requisite. So relaxor entities or polar nanoregions, which I already introduced as the second necessary condition. And third, so these relaxors are pretty close by energy to the classical ferroelectrics, and in principle, ferroelectric order can be induced in these materials below a certain temperature after coiled by a high enough electric field which exceeds a critical transformation. And in some materials, we can even observe a spontaneous transition from the relaxor to the ferroelectric state. So, and examples of the relaxor, for example, one example is, as I say, PMN. When we have this PMN with another, so we introduce also zinc, which is also divalent but has different size of magnesium. And so we have disorder. This is typical loop. And for example, for such a thin films in the system, one reported very large recoverable energy density of about 60 joule per centimeter cubic. Even larger was reported for this another relaxor system, where we substitute now not P side of the perovskite structure, but A side. We replace D-variant lead by 3-variant lanthanum, and in this thin films, actually a very large field. So since the films, we can apply large fields. So you see, here is 600 kilovolt per centimeter, and here is almost 4,000 kilovolt per centimeter. It's actually a huge field, and this huge field we can have even 65 joule per centimeter cube. So this is nice materials, but problem is that they contain lead. I don't know what is the situation in Brazil, but in Europe, our governments decided that we should remove lead from the future electronic components. So the research now is, let's say, focusing to find lead-free materials which can have such a nice characteristic as lead-contained materials. And therefore, for example, what we are looking for, we're looking for materials based on the barium titanate, which is well known ferroelectric. So the system, barium titanate with tin. So tin already make materials, barium titanate slightly relaxor. And we also add this bismuth yttrium O3. And why we add bismuth yttrium O3? Since bismuth, like lead, is very particular cation. Both these cations, bismuth 3 plus and lead 2 plus, they have so-called lone electron pair. This lone electron pair can make a strong covalent bond with one of the neighbor oxygen, and therefore the cation is shifted from the central position in this octahedral environment, and therefore dipole moment is created. So people call such cations like ferroelectrically active cations. So lead is one of the most known, therefore the lead-contained ferroelectrics are so good, and bismuth is another material. Therefore, we introduce bismuth to induce also increase our dipole moment. So this is like behavior change in the composition with more bismuth yttrium oxide. So you see, we start from classical ferroelectric behavior for barium titanate. Then our peak becomes broader and broader. Finally, it becomes strong broad and also strong frequency dependent. So we have transition to relaxor behavior. And when we now calculate from the bipolar hysteresis loops our energy storage parameters, so you see here black points correspond to the recoverable energy density, and the red points correspond to the efficiency eta. You see that these materials, like this 8% of the bismuth yttrium oxide, is very good. It has large energy density and also large efficiency. So of course, this energy density is still less than I show in these films, but these are films and these are bulk ceramics. So electric field is still pretty low. It's only 150 kilowatt per centimeter in comparison to 4,000, which were shown before. So other materials, for example, this people from, I think it was from Penn State, they studied system of barium titanate with another bismuth compound, bismuth scandium oxide, and they have thick ceramic films with thickness of 27 micron, and they can reach the high energy density with field of 1000 kilovolt per centimeter. So they can reach about 7 joule per centimeter cube. And what also was interesting is this high energy density parameter was stable in the broad temperature range, which is very important for the application. You should have this large numbers not on the narrow temperature window. For application, we also need the material have to be work stable in the broad temperature range. So just comparison between different materials taken from literature based on the different ferroelectric systems. So what we can say about relaxor ceramics, they usually have good energy density, and in principle efficiency is also okay, but typically these relaxor ceramics have large dielectric permittivity, and therefore they have low breakdown strengths. So then another materials, antiferroelectric materials. So again, I don't know if you know the term antiferroelectric, but some of you can know what is antiferromagnets. And antiferroelectric is kind of analog of the antiferromagnetic material. So again, in the ferroelectric materials, we have a long range polar order. It means that when we have a large single domain, all polarization moves in the same direction. In an antiferroelectric, we will have kind of unit cell, and we will have change of the local dipole moment to the opposite side from unit cell to unit cell. So in principle, this is schematical picture of antiferroelectric state. So adjacent dipole moments are antiparallel. So what is typical feature of antiferroelectric is so-called double hysteresis loops. What it means, so we start from this anti-polar configuration, which actually has low dielectric permittivity and low polarization, and we apply the electric field. And above some critical electric field, we switch dipole moment of one sublattice along the field. So we induce the transition from antiferroelectric state to the ferroelectric state, and this is accompanied by a jump of the polarization. And then when we will decrease the field, since this induced ferroelectric state is actually metastable or thermodynamically unstable, then below the another critical field, which is actually lower than the first one, we will have transition back to the antiferroelectric state. So zero remanent polarization, small dielectric permittivity at low fields, and large induced polarization are good for energy storage. And classical example of the antiferroelectric material is lead zirconate, again lead contained, unfortunately. So this has transitioned to the antiferroelectric state about 230 degrees C. And this is one example of thin films of lead zirconate with different orientation. And you see that the critical field as well as maximal polarization depends on the orientation of the films, and therefore the energy density will also be different for different orientation. But for 111 oriented zirconate, lead zirconate films, we have the energy density about 11 to 12 joule per centimeter cube, and fields about 500 to 700 kilovolt per centimeter. And you see again, the initial energy density is low, but then when we have a transition to the ferroelectric state, we have a jump-like increase of the energy density. So, what is important? Important that we have to induce the transition to the ferroelectric state at relatively low electric field to avoid the dielectric breakdown. So this critical field should be not high enough. On the other side, when this critical field will be too small, it means that the state, the induced ferroelectric state, will be metastable. And when we go back, the transition to the antiferroelectric state will be not complete. So when we remove the field, we will still stay partially in the ferroelectric state. Part material will be antiferroelectric, but part of materials will remain ferroelectric. And therefore, instead of this nice picture with zero remanent polarization, we will have a kind of polarization loop with twice. And you see when we, for example, will add barium to the lead zirconate, we will increase so-called tolerance factor. Tolerance factor is actually a geometrical factor to describe the packing of a cation to superoxide structure. And this increasing of the tolerance factor will stabilize the ferroelectric phase. On one side, we will decrease this critical field. is good. From other side, the ferroelectric state will be finally so stable, then the remanent polarization will be growing up with the increasing amount of barium. So again, we have to keep a balance. So critical field should be not low, but the ferroelectric state should be also not so thermodynamically stable. Then when we remove the field, it should disappear. Yeah? So and therefore people play with chemistry, with doping of, for example, lead zirconate to found the optimal compositions. So it's one example here. One can add tin, and tin will strongly reduce this critical corrosive field. And you see, for example, here quite a complex materials. We have strontium and lanthanum on A side, zirconium, titanium, and tin in the B side. And but we can find a composition with pretty also good parameters. Field about only 300 kilovolt per centimeter in comparison to 600 in the lead zirconate, and about 5.5 joule per centimeter cube the stored energy density. But what is not good for antiferroelectrics, sometimes this hysteresis is too broad, and therefore the efficiency will be low. So you see, efficiency is here is only 0.7. So we can introduce, for example, more. We take out strontium, change concentration of tin, introduce more tin, and we can reduce this hysteresis. Therefore, so you see the efficiency is going up, but in parallel the stored energy goes down. So, and when you will look now in literature about the energy storage, these parameters, they're always kind of contraplane. When the stored energy goes up, the efficiency goes down. When you would like to have a large efficiency, your stored energy will be less. So you always again have to find a compromise. Another example of antiferroelectric is silver niobate. Just to show you shortly, it has also at low field almost linear behavior, but when we increase the field, we have a transition into ferroelectric state, which is partially goes back to the antiferroelectric, but finally a significant amount of ferroelectric phase remains when we decrease the field. Again, this material is not bad, it's good for energy storage, and when we will dope this with manganese, we can reduce this amount of the remaining ferroelectric phase, so we can reduce the remanent polarization, and correspondingly our efficiency will increase from 40% to 55%, and at the same time the energy, stored energy will also increase. So in this material, when we replace niobium not with magnesium but with tantalum, people show that again the temperature stability of energy storage parameter will be good. So we have recoverable energy about 4.4 joule per centimeter cube in pretty broad temperature range, and also our efficiency is more than 60%. And finally, so I was speaking about relaxors, and I was speaking about antiferroelectrics, and people try to combine these two concepts. They try to find an antiferroelectric relaxor material which will combine advantages of both antiferroelectric and relaxor materials. So slim double hysteresis loops, for example, in this system of sodium bismuth titanate, barium titanate, or more complex system when we add to these materials also another component, strontium bismuth titanate. So you see, in this material we have pretty ideal case. We have a double hysteresis loop, but this double hysteresis loop is very slim, so the area of hysteresis is very small. The efficiency of this material stay about 90%, about 80%, with energy density about 40%. Okay, and this is for the multilayer capacitor material, so this film thickness of the layer thickness of 20 micron and the electric field of 350 kilovolt per centimeter. Do we have more time? Okay, good. So,
5 minutes.
yeah, about polymers. So, ceramic materials are good, but ceramic materials has a problem of the breakdown strength. There are other kind of ferroelectric materials which are not ceramic but polymers, and polymers can withstand much larger electric field than ceramic and even than the ceramics. Therefore, there is a lot of research on the electric energy storage in the polymers. And when we speak about ferroelectric polymers, we always speak about PVDF or polyvinylidene fluoride. So in these materials, we have such chains, and we have fluorocarbon and fluorohydrogen bonds, and this fluorocarbon bond is strongly polar and has own dipole moment. And when we have a specific information of this polymer, so-called beta phase, then the dipole moments of the individual bonds are ordered. So we have long range order, we have ferroelectric state. So again, we have ferroelectric polymer, and even better when we add trifluoroethylene as a copolymer, but this is ferroelectric material. And we say that ferroelectrics are not good for electrical field storage. Therefore, we have to destroy this ferroelectric state, and one of the strategy to induce another monomer, for example, chlorofluoroethylene or chlorotrifluoroethylene. So then we have kind of terpolymers like this one or like that one, and these terpolymers, they show typical relaxor behavior. They show slim hysteresis loop, they show broad peak of the dielectric permittivity and strong frequency dispersion of the dielectric permittivity. So this is one example of these terpolymers with different content of third monomer of chlorofluoroethylene. You see, when we increase the electric field, our polarization is going up. The area between the polarization axis and field axis increases, but at the same time also hysteresis increases. As I said, we increase our stored energy and we also increase our losses simultaneously. So these are parameters for this polymer. So discharge energy density, efficiency, and you see that for this polymer, terpolymer with 7% of CFE, at the field of 200 kilovolt per centimeter, we can reach the stored energy density about 5 joule per centimeter cube, which is pretty good. And correspondingly, the efficiency will be still above 60%, which is also not bad. So how we can improve these properties further? So we can combine polymers and ferroelectric ceramics. So polymers have high breakdown strengths, but they have low dielectric permittivity as compared to the ferroelectric ceramics. So we can combine them. We can make a composite. We can make a composite which consists of polymer matrix and ceramic particles. And even better when we use not just large particles, but nanoparticles. So in that case, we will have material with large dielectric permittivity, larger than the pure polymer, and better breakdown strength than pure ceramic. So we will have we will take advantages of both kind of materials. So people use different kind of fillers, nanoparticles, nanofibers, nanosheets. Of course, the dielectric properties depends on the volume fraction of the fillers, on the interface between the filler and polymer matrix, on the geometry of the fillers. Also, if we have nanoparticles, nanofibers, or nanosheets, we'll have different examples. So different situations. One example is here. We have PVDF CFE with nanoparticles of barium titanate zirconate. And you see when we increase the amount of the nanoparticles, here's volume percentage, the dielectric permittivity of our materials also increases. And we measure this unipolar hysteresis loop, and we calculate also the discharge energy density and efficiency. And again, you can see that material with the moderate amount of the DCT fillers have very good energy storage, about 4 to 5 joule per centimeter cube, so it fills about only 120 kilovolt per centimeter. And again, efficiency is okay, above the 50%. So here we can see how it depends on the barium titanate content, more in details. So again, as I said, moderate adding is the best properties, and then the stored energy becomes smaller, and the efficiency also deteriorates. Okay, I would like to summarize my presentation. So typical ferroelectrics are not suitable for energy storage due to their large remanent polarization and polarization hysteresis. The relaxor ferroelectrics have a high dielectric permittivity, slim polarization loops, and very low remanent polarization. They exhibit very high energy efficiency, but their breakdown strength is usually low due to large dielectric permittivity and large electrostriction. Antiferroelectrics are very promising for energy storage due to their double hysteresis loops, but pure double loops with negligible remanent polarization have not often been observed. And important is the phase competition between ferroelectric and antiferroelectric state in these materials. So polymer ceramics composites combine advantages of polymers and ceramics. They are reliable, they have self-healing ability, but their manufacturing costs are still challenging. And when we speak about the optimal geometry, the multilayer capacitors will be optimal materials, since they combine, let's say, large active volume of material and possibility to duplicate application of very high electric field. And employ new dielectric materials with high break dielectric strength, thermal stability, and moisture resistance, as well as optimizing the fabrication process, are potential ways to improve the reliability and stability of such multilayer capacitors. So, muito obrigado para a sua atenção. Thank you very much for your attention.
Questions, please?
I have at least one. First of all, thank you very much for your presentation. It was very interesting and didactic. My curiosity is about the size of the ceramic particles or nanoparticles to be used in that composite, polymer composites. You know?
Okay, typically we deal with ceramic, with nanoparticles. There is kind of, usually the interplay. So from one side, you would have to have a particle with large dielectric permittivity. And you know there's a size effect. As you will decrease the particle size, your dielectric permittivity will also go down. So from other side, you would like to have really good distribution of nanoparticles in your nanopolymers. The nanoparticles has to be small enough to don't introduce many mechanical stresses in the polymers, since in that case we will have, let's say, degradation of properties of polymers. And amount of the nanoparticles should be also controlled. The volume fracture should be not high enough. Again, high volume fracture will introduce more defects. And finally, can come to the percolation effect, which we will also talk about. So, finally, you have to find an optimal. You should decrease the nanoparticle size, but not go too deeply to don't, let's say, lose the good dielectric properties. So, in our case, we use nanoparticles with size, say, between 50 to 100 nanometers.
Oh, nice. Yeah, I asked it because we have used solution polyspin here to make fibers, and our fibers are about 200 and 500 nanometers in the diameter, and some micrometers long. So that was my. And only a curiosity, because here we have sun, a lot of sun, and now we are starting in this region to have some solar energy production. But I was reading that the problem of solar and wind energy is the production, because those kind of production is not continuous, and then can produce some kinds of instabilities on the line, on the transmission. So that's one of the reasons that we are studying lots of this kind of storage energy.
It's like I tried to introduce in the beginning that why we look for the energy storage, since for this renewable energy sources we need a good, let's say, storage capability. And of course, we can use it also for portable devices, and we can use it in the automotive, for the cars.
Of course.
Not only for the energy harvesting, and energy, let's say, generation.
Thank you.
These ceramics and polymer composites, does the polymer need to be polar? The polymers have to be polar or not?
Not necessary. Not necessary. But okay, the question again, so we would like to have large dielectric permittivity.
Yes.
And when we will have a non-polar polymer, even when we will add ferroelectric ceramic, the improvement of the dielectric permittivity will be not so much. Okay. Just to give an idea, so you see, we started from the beginning, we have about 50 relative permittivity, and we can improve it twice. But if you start from 5 or 10, you will obtain still not very high value. But I think there is also research in with non-ferroelectric polymers. Just linear dielectric.
How does the dielectric breakdown compare between polar polymers and non-polar polymers? Because I think that non-polar polymers might present an enhanced dielectric breakdown strength.
Yeah, it might be. I don't have numbers in my head.
Okay.
I cannot answer directly, but you are right. So they could be. But again, we can have linear dielectric from the beginning. We can take CO2 or CO2 or something even simple aluminum oxide. We'll have good breakdown strengths, but due to very small dielectric permittivity, we will not store much energy inside.
Does the polymers also, the breakdown dielectric strength also follows a Weibull distribution for polymers? Also?
Yeah. Weibull distribution is kind of, I think it's statistical model, it's in materials free. So actually, it's come from mechanics, from the structural mechanics.
I asked this because I'm more familiar with the concept of variable distributions being applied to fragile materials, not polymers themselves. But
Okay, of course, from the mechanical point of view, it will be different since elasticity of polymers appears quite fast, and let's say they have different kind of mechanical deformations than the ceramic material, but electrically they are not so different. And we speak about electrical breakdown, not about mechanical.
okay, thank you.
Questions? I have just one technical question. If we are talking about materials, of course, at some moment we need to think in applications, technological applications. Okay? Can you give us a commercial example of applications, of success application on this material for storage energy? I don't remember. I asked you because I
cannot give you now. But okay. So let's say if you consider capacitor, just the electric capacitor as a material, as an element where we store electrical energy in normal circuit. So we have plenty of ferroelectric capacitors based on barium titanate, based on PZT, based on other ferroelectric materials. But that energy storage, high energy storage sensor, I will look for this example. I don't have it in mind.
Okay.
Thank you for your comment.
Okay. Can we finish? Okay. Let's thank the speaker again. And just to finish, I will remember in the next week we have the short course. The interested must apply in the post-graduation course, I suppose.
Yeah, I suppose to. Yeah, we are trying to.
We are going to we program the course, including a theoretical part first, and if it will be possible, we experiment
some practical,
because we have in the department an AFM microscope. Okay. My opinion, Dr. Schwarzman is one expert in atomic force microscopy techniques, especially to characterize different materials like ferroelectric, multilayer, piezoelectrics, and polymers. Okay. So
polymers is difficult.
So I think it will be an important opportunity for the students to contact and to discuss personally with the Professor Subhasu. Okay?
Okay, but this will be just a kind of course for students, so more didactic.
It is important to remember that in the finish of all classes will be served snacks and
Great.
so I'm kidding. Ok, pessoal. Obrigado então mais uma vez.